last thing that we need to talk about with this is is basically the fact that in this image, the earth and the bowling ball are pulling with the same force. So the earth is holding the bowling ball, but the bowling ball is also holding the earth. Okay? And that doesn't make sense a lot of time, okay, until you really start to explain Newton's third law. So really briefly, here is a review of Newton's third law. Newton's third law says forces are equal and opposite. Okay? They have to be force pairs. So two objects that are interacting with each other, if this hand is pushing on this hand, then this hand is pushing back with the same force, okay? A better example might be, I put my laptop on the table, force of gravity is pulling the laptop down, but the table is pushing back with an equal force, okay? So one way to figure this out, because it gets really confusing real quick, is I write it down. What's the force acting? So the causer of the force, the laptop, is causing a force on the table, which means the table also causes a force on the laptop. So all I did was flip-flop these words. I just flip-flop these words to find what the force pair is. So here's table here, and here's table here. So we just switch it, okay? So if a car hits a wall, we could say the wall hit the car. And this is classical relativity in physics, actually. So perspective makes a difference, and sometimes it doesn't. So if I'm sitting in the car and I watch the wall come and hit me, if I put a camera on there, I would see that. But I could put a camera on the wall and see the car hit me, okay? So the forces are actually going to be equal to each other. Okay, now here's what messes people up. The forces are equal and opposite, but the reaction to the force can be different. It can be the same, but it can be different. So we have an astronaut pushing on a ball in space, and the ball, in a sense, is pushing back on the astronaut, and the forces are equal. The force of the astronaut on the ball and the force of the ball on the astronaut. That force is equal, so they're both equal to 100 newtons, so for pretend, okay? But we also know that force equals mass times acceleration, mass times acceleration. Well, let's say the astronaut has a mass of 100 kilograms, and the bowling ball or the ball has a mass of 1 kilogram. So for this to be 100 newtons, what must be the acceleration of the astronaut when he pushes? So 100 times 1 equals 100. So that's 1 meter per second squared. But the bowling ball is 1 kilogram. And so when it pushes, its acceleration is going to be 100 meters per second squared. Okay? So the force is the same, but their reaction to that force, their acceleration based on that force is going to be very, very different, okay? So we can have same forces, but very different reactions. So let's look at gravity and the earth. So the earth pulling on the bowling ball and the bowling ball on the earth is the same force, and it's pulling with the same amount, 9.81 newtons. We just calculated that. Okay, but the reaction to that force is very, very different. So what's the acceleration of the earth? Well, if you plug that in, I don't even know if Desmos will give us a very tiny, tiny, tiny number. But this one, what would we do? 9.81 meters per second squared. So the bowling ball has the acceleration due to Earth's gravity. Okay, so if we go into Desmos, let's say 9.81 divided by 5.972 times 10 to the 24, highlight those numbers and exponent them. This is the answer, 1.6764 times 10 to the negative 24. So that means the acceleration due to Earth caused by the bowling ball is 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 1, 6, 4 meters per second squared. Okay, so the Earth does have an acceleration because of the bowling ball, but it is practically insignificant, okay, compared to what happens to the bowling ball. So we don't really see it, okay? So this actually applies to the Earth and the Sun. So the Earth and the Sun are pulling on each other with the same force. So the Sun actually, not because of the Earth, but because of all the planets, the Sun actually wobbles back and forth where it's at because the force of gravity of the other planets causes it to move. That's actually how we find exoplanets, or one of the ways for close exoplanets is we can actually see the wobble of the stars, and there must be planets there. The forces are equal and opposite, but the reactions to those forces are different. And this is actually why when NASA took Pluto off the list of planets, what it was saying is, basically what I'm saying is, its gravity has to be enough that it clears its orbital path. In other words, the Earth's mass is so large that any objects that come across its path will be deflected or even pulled into the Earth, okay? And that's because of this right here. Because the effects of other objects they're generally so tiny, it doesn't do anything to the Earth, but it causes something to happen to the object, okay? But they're both pulling on each other. That is Newton's law of gravitation. What you're going to really be asked to do is, you're going to be asked to identify the pieces of the equation. You're also going to be asked, what happens if I double the mass? What happens if I double the distance? What happens if I halve the mass or decrease the mass? Okay, so we're just using our math logic to explain the problem and not having to do the full calculation. So my suggestion to you is write the equation and then plug in the numbers like this and then find what is it out here that goes in front. And then you should be able to answer the questions. That's all I've got. Have a great day. Thank you.